Okay, let's look at the next example. Question 32, page 444. It says that show that if n is a positive integer, then 2n choose 2 is equal to 2 times n choose 2 plus n squared. Part A, using a combinatorial argument, and part B by algebraic manipulation. Okay, so in combinatorial argument, we want to prove an identity, and of course, each identity has left-hand side and right-hand side. So left-hand side, we say that, left-hand side, it counts number of something. And if we show that right-hand side, it also counts the number of same thing, then we can say that therefore those two quantities must be equal. So in this question, let's look at the left-hand side is 2n choose 2. So 2n choose 2 represents the number of ways to choose 2 objects out of 2n objects. If we have 2n objects in total and we want to choose 2 of them, then the number of ways we can do that is 2n choose 2. So part A, solution, left-hand side equals 2n choose 2, counts the number of ways to choose 2 objects out of 2n objects. Say, let's say we have 2n objects. Let's call them, let's assign letters to them. Let's say, for example, I can call them A1, A2 to A2n. 2n objects, and I want to choose 2 of them. In how many ways can I do that? In 2n choose 2 ways. Now, if I show that right-hand side is also number of ways to choose 2 objects out of these 2n objects, then the identity will be proved. Now, for right-hand side, I want to show that it also counts number of ways to choose 2 objects out of 2n objects above. Now, in order to choose 2 objects, let's divide the total objects, which is A1 to A2n. I want to divide them into 2 groups, A1 to AN, the first n objects, and AN plus 1 to A2n, the next n objects. Let's divide A1 to A2n into 2 groups, A1 to AN and AN plus 1 to A2n. Now, now we have different options. Basically, now I can say this way. Now we have 3 options to choose 2 objects. What are my 3 options? The first option is to choose both. I want to choose 2 objects, right? I can choose both those 2 objects from the first group, or I can choose both of those objects from the second group. And my other option is to choose 1 object from first group and 1 object from third group, 1 object from second group. Right? There is no other option. I have 2 groups of objects, and I want to choose 2 objects. Either both those 2 objects must be in the first group, or both of them must be in the second group, or 1 from first group, 1 from second group. There is no other possibility. So first option or first possibility, choosing 2 objects from the first group which is A1 to AN. How many ways do we have to do this? We have N choose 2 ways to do this. I have N objects. I want to choose 2 of them. In how many ways can I do that? N choose 2. N choose 2 counts number of ways to choose 2 objects out of N objects in total. My second option is to choose 2 objects from the second group. Second group means AN plus 1 to A to N. Again, we have how many ways to do this? But again, we have N objects, right? AN plus 1 to A to N. There are N objects. And I want to choose 2 of them. So N choose 2 ways to do this. And my third option is to choose 1 object from the first group A1 to AN, and 1 object from the second group AN plus 1 to A to N. This can be done in how many ways? See, I want to choose 2 objects, right? So for the first one, we have N choices to choose first object, and N choices for the second object. Number of choices to choose first object, and this is number of choices to choose second object, right? For first object, I have N objects in total, A1 to AN. I want to choose 1 object, so I have N choices. And for second object again, I have N objects, AN plus 1 to A to N. I want to choose one of them. So I have N choices again, right? N choices for the first object, N choices for the second object, and therefore N times N, a product rule. If I can do 1 task in N rules, N ways, and second task by M ways, in total I have N times M ways to do overall of those two tasks. So I have n choices to choose first object, n choices for to choose second objects. Overall, I have n times n, or n squared ways to do this. I am multiplying them by product rule. So overall, to choose two objects out of 2n objects, we have how many ways? I counted how many ways we have in option number 1, in option number 2, and option number 3. So I just need to add the number of ways in each of those options, and therefore I will get n choose 2 ways for option number 1, n choose 2 ways for option number 2, n squared ways for option number 3, and that's 2 times n choose 2 plus n squared, which is my right-hand side. So we show that left-hand side is the number of ways to choose two objects out of 2n objects. Right-hand side is also number of ways to choose two objects out of 2n objects. Therefore, we can conclude 2n choose 2 equals 2 times n choose 2 plus n squared. Both left-hand side and right-hand side represent number of ways to choose two objects out of 2n objects. Okay. Now part B is very simple. We can prove this identity algebraically. So left-hand side, let me start with the right-hand side maybe. Right-hand side says 2 times n choose 2 plus n squared. Well, we have a formula for n choose k. N choose k. What was it? N factorial over k factorial, n minus k factorial. So this is going to be 2 times n factorial over 2 factorial, n minus 2 factorial plus n squared. Now this is going to be 2 times n factorial over n minus 2 factorial is n times n minus 1. And 2 factorial is 2. Say n factorial over n minus 2 factorial. N factorial can be written as n minus 2 factorial times n minus 1 times n. So n factorial, we can write it this way. So n factorial over n minus 2 factorial, therefore will be n times n minus 1. And then 2 factorial is of course 2 plus n squared. So if I take common denominator, common denominator is 2. 2n times n minus 1 plus 2n squared. And then this is 2n squared minus 2n plus 2n squared divided by 2. This is 4n squared minus 2n divided by 2. 2n I can factor times 2n minus 1 divided by 2. And again, this one we can write it as 2n factorial divided by 2. 2 I can write it as 2 factorial times 2n minus 2 factorial. Again, because 2n factorial divided by 2n minus 2 factorial is 2n times 2n minus 1. And 2 is same as 2 factorial. And this one, again, is 2n choose 2. Because 2n choose 2 is 2n factorial over 2 factorial, 2n minus 2 factorial, and this is my left-hand side. Okay, so algebraically it was simple. Just write down the formula and then take common denominator. Start with the right-hand side, get to left-hand side, or you can, of course, start with the left-hand side, get to right-hand side. Okay. Okay, and the last example we want to do today, question 7, page 608. So determine whether the relation R on the set of all integers, the relation R on the set of all integers is reflexive, symmetric, antisymmetric, and or transitive. Where x and y, the pair x and y belongs to the relation R if and only if, and part A says x is not equal to y. Okay, so we are defining a relation. The relation R is on the set of integers, so that means x and y both come from the set of integers z. And we are saying that x and y, the pair x and y belongs to R if, now part A says if x is not equal to y. So if x is not equal to y, then the pair x and y is in R, otherwise it's not in R. So for example, 2 and 2 is not in R because 2 is equal to 2. But 2 and 3 is in R because 2 is not equal to 3. So we want to know whether this relation is reflexive, is it symmetric, is it antisymmetric, is it transitive? So solution, reflexive, R is not reflexive because, for example, 1 is not equal to 1, and 1 is equal to 1. And so 1 and 1 does not belong to R. Reflexive means A, and A must be in R for every A in our domain, which is Z here. If A and A is in R for every A, then we can say that the relation is reflexive. So, but here 1 and 1 is not in R. Why 1 and 1 is not in R? Because 1 is equal to 1. But in order for a pair to be in R, x must be not equal to y. In other words, 1 not equal to 1 is not correct. So that means 1 and 1 is not in R. Is not in R, so it's not reflexive. What about symmetric? R is symmetric. Since x and y in R implies that x is not equal to y, and this implies that y is not equal to x, right? If x is not equal to y, of course, y is not equal to x, and that means y and x is in R as well. So whenever you can conclude from x and y in R, you can conclude y and x is in R. That means your relation is symmetric. Antisymmetric, R is not antisymmetric since let's say 2 and 3 is in R, and 3 and 2 is in R as well, but 3 is not equal to 2. Recall, R is antisymmetric if A and B belongs to R and B and A belongs to R, implies that A is equal to B for every A and B. Antisymmetric means whenever A and B and B and A, both of them are in R, A must be equal to B. If you can conclude from A and B and B and A, both of them being in R, if you can conclude A must be equal to B for every A and B, then it's antisymmetric. But here, 2 and 3 is in R because 2 is not equal to 3. 3 and 2 is also in R, again, because 3 is not equal to 2. But of course, 2 is not equal to 3. So this definition does not hold here for this example. Therefore, R is not antisymmetric. What about transitive? R is not transitive. Why? Because 2 and 3, for example, 2 and 3 is in R. 3 and 2 is also in R. But 2 and 2 is not in R. Again, recall about the definition of transitive. R is transitive if A and B in R and B and C in R implies A and C in R. Again, for every A and B and C. But here, 2 and 3 is in R, 3 and 2 is in R, but 2 and 2 is not in R. Why 2 and 2 is not in R? Because 2 is equal to 2. R only contains the pairs X and Y, where X is not equal to Y, but 2 is equal to 2, so 2 and 2 is not in R. Okay, so this was part A. Let me do one more part. Let's say part B. X, Y bigger than or equal to 1. So we are saying that X and Y belongs to R if and only if X times Y bigger than or equal to 1. So for reflexive means A and A must be in R for every A. Is that true? A and A will be in R if, according to the definition of this relation, A and A is in R if A times A is bigger than 1. A times A means A squared. So can I say that A squared is bigger than or equal to 1 for every A coming from the domain, which is the set of integers? Well, A equals 0 does not satisfy A squared bigger than or equal to 1, right? So this one, we can say that R is not reflexive since 0 and 0 does not belong to R, because 0 times 0 is 0, which is not bigger than or equal to 1. So it's not reflexive, because for reflexive, every A and A must be in R, but here 0 and 0 is not in R. Symmetric. Symmetric, R is symmetric because if A and B is in R, or let me say if X and Y is in R, doesn't matter, then this means that X times Y is bigger than or equal to 1, right? Because R contains of all pairs X and Y such that X times Y is bigger than or equal to 1, right? So if X and Y is in R, then X times Y is bigger than or equal to 1. And this, of course, implies that Y times X is bigger than or equal to 1, right? Because X times Y and Y times X are the same thing. And Y times X bigger than or equal to 1 means Y and X is in R. So we show that if X and Y is in R, then Y and X is in R. And that means R is symmetric. What about anti-symmetric? Anti-symmetric, R is not anti-symmetric. Because, for example, 2 and 3 is in R, and 3 and 2 is in R, but 2 is not equal to 3. Remember, again, for antisymmetric, we need to have, whenever A and B is in R, and B and A is in R, then A must be equal to B. But here, 2 and 3 is in R, 3 and 2 is in R, but 2 is not equal to 3. Why is 2 and 3 in R, by the way? 2 and 3 is in R because 2 times 3 is 6 bigger than 1. 3 and 2 is in R because 3 times 3 is 6 bigger than 1 as well. And what about transitive? Transitive, so if let's say A and B is in R, that means A times B and B in R means A times B bigger than 1. B and C in R means B times C bigger than 1. So from these two together, can I conclude that A times C, A times C bigger than 1? If A times B is bigger than 1, and B times C is bigger than 1 as well. And remember, A, B, and C are all integers. Can I conclude that A times C is also bigger than 1? Well, again, to answer this question, we can think about some examples and some numbers for A, B, and C. Try to construct a counterexample. If you couldn't construct a counterexample after a lot of inspection and considering all different values for A, B, and C, whether positive or negative, then you can try to prove it. And in that case, you have to prove in general. But here we can basically construct a counterexample easily. So this implication is not valid, cannot conclude, or cannot, you cannot conclude. See below. So a counterexample that shows the implication above is not valid. So let's say, for example, 2 times 3 is bigger than or equal to 1, right? As if I choose my A to be 2, B to be 3, 2 times 3 is bigger than or equal to 1. Now 3 times 1 over 3 is also bigger than or equal to 1. So here A is 2, B is 3, and C is 1 over 3. So 2 times 3 is 6, bigger than or equal to 1. 3 times 1 over 3 is 1, bigger than or equal to 1. But what will be A times C? But A times C will be 2 times 1 over 3, which is not bigger than or equal to 1. So A times B is bigger than or equal to 1. B times C is bigger than or equal to 1. But in this case, A times C is 2/3, which is not bigger than or equal to 1. So we show that R is not transitive. Show that R is not transitive. Since 2 and 3 was in R, and 3 and 1 over 3 is in R, but 2 and 1 over 3 is not in R. Okay, so I did 2 parts for this question, A and B. There are other parts as well, which you can do as exercise. Okay, guys, so these were some sample questions for, or practice questions, basically, for different chapters of the book and different topics that we covered in this course. Okay, guys, so see you next week on the final exam day. I'll send you one more email about reminder about the exam day and time. Okay, guys, so thank you and see you soon.